All right. Morning, guys and gals. Can you type something on the chat box if you can hear me? You hear me, guys? Okay, thank you. Thank you, Lindsay. We'll start 11:05 in case some of your classmates would like to participate. Kahoot in, please. The coverage of this quiz is will come from the last two videos. So it's about the thread introduction to threads and thread API last Wednesday. Hi, Gaisel. There will be 6 questions, three from last Friday's video and three from last Wednesday. Start at 11:0. Yeah, 11:04, 11:05. Hey, so let's get ready. Okay, we'll start the game. Quiz 4. Okay, so the correct answer is global variables. The global variables in the program, the process, are shared by the different threads in the process. So each thread will have its own stack, its own program counter, and the values of. Okay, Perfinian, 5L. Next. It seems that I just realized that this question has some ambiguity in it. Anyway, can answer. So the correct answer is scalability. Okay. So that's why I was thinking about the ambiguity, but the correct answer is scalability. So if you have multiple cores or multi-cores, then you can run threads on this. Next. Okay, Perfinian again. Next question. Yes, it started already. Quiz started already. Jotam, the quiz started already. Okay, so the correct answer is many to one. So the first part, many, is the user thread and one is the kernel thread. If you only have one kernel thread for that group of user threads, if one user thread blocks, then the others will also block. Okay. Next question. All right. The correct answer is load balancing. So in multi-core programming or in parallel programming, uh, you don't want one core to be overburdened with jobs, so you try to balance the load and distribute the jobs among the different or the multiple cores. Okay. Alan, 5L. I hope you can bring your lab section to the podium. Next question, true or false? One chance of answering, getting the correct answer. Okay, the correct answer is true. So that's why threads are preferred over process creation, calling the fork system. Bautista. Next, last question. Okay, the correct answer is set jump. Okay? In the video, there is an example in the folder, in the source code folder, we have the user level folder. Then I have an example there of implementing a user level threads, which basically uses the set jump and its partner function called long jump. Okay, so let's see the winners. Okay. And the winner is Bautista from CD2L. Congratulations, Bautista. Okay. And congratulations also to the runners up, Cruz and Perfinia. Okay. So hope you had fun and you're able to test your knowledge last two videos. Okay, so some announcements. For the exam, so we're going to have a tryout or a trial exam, okay, on Monday. So just to test whether the setup will work. So the same time. So I hope everyone will make you will make yourself available on the date and time for the exam. Okay, and I will just post the details of the process, the mechanics on. Okay, so let's move on to today's topic, which is the last part of threads. Okay, so threading issues. Okay, so in the previous videos, we were talking about implicit threading. Implicit threading is just a way to lessen the burden of the programmer of manually creating the threads, managing the threads, and many other stuff. So implicit threading would basically, okay, I want this task to be executed in parallel. Okay, the system or the framework will provide the threads, and it's the system or the thread library that will manage the thread creation and destruction. So example, we have thread pools, we have OpenMP. In OpenMP, we simply put in some directives, preprocessor directives on the code to mark a specific region to be treated as a thread function. And compiler, GCC, will generate the corresponding code to execute that code fragment in a thread. So the programmer doesn't need to do some thread create, thread join, etc. Okay. So, and in Java, we have the executor service wherein you can actually pick out a thread from a cache of threads and then use that to execute given task. Quite easy for the programmer. Now, there are other issues regarding threading. So we already know the benefits of threading, multiple threads. Now, let's look at some of the other issues regarding threading. First one is called, we have several. So we have the semantics of fork and exec, handling, thread cancellation of target thread, thread local storage, and scheduler activations. And we're going to look at each of these issues. So let's start with the semantics of fork and exec. So remember that fork and exec are system calls. The fork system call will create a new process, and the exec system call will override the program. Will actually a loader which will load the executable to the memory allocated to the process, basically overwriting the contents of the parent process. Okay. So regarding threads, if you implement threads, one question that will come to mind is, does the fork duplicate only the calling thread or all the threads? So remember, you have a program which uses threads, and in your program, in your main program, after you created threads, call the fork system call to create a new process. Now, when you create the new process, will the new process contain or duplicate all the threads from the parent process or not? So in some Unix systems, they actually have two versions of fork. One is it does not duplicate the threads, and another version duplicate the threads which are running on the parent process. Okay, so that's the idea. So to solve the problem, you implement two versions of fork. If you want a program that will inherit the threads, you use the version that forks with that will duplicate the threads in the parent process. So the exec system call, on the other hand, will usually just work as it is, because after creating the process and you call exec, okay, everything about the parent process will be done. So no problem with the semantics of implementing exec system call. Okay, so that's the idea. The next one is signal handling. Okay, so what are signals? Okay, signals are used in Unix system to notify a process that a particular event has occurred. An example of this signal is when you press Ctrl+C, or whenever you kill a process using the kill command. And usually, each process will have a signal handler that will, you can think of the signal handler as an event handler in Java. Okay? So a signal handler is used to process signals, and it is generated when an event occurs, like pressing Ctrl+C. And that signal is delivered to a process. There are actually two types of signals. We have the synchronous and asynchronous signal. When you say synchronous signal, let's say your program divides by 0, then when your program divides by 0, the process will be informed, hey, your program, you performed division by 0. So that is an event, and a signal will be sent to the process telling it that, hey, you divided by 0. That's asynchronous. But the asynchronous one is something external from the running process. You will send a message to a running process. So that when event happens, a signal is generated, and that signal is delivered to the process. And there are two types of signal handlers actually. So when, let's say, when Linux creates a process, it creates a default signal handler such that when you press Ctrl+C, your program will terminate. Okay? There is a default handler that will process that. Okay? And it can also be overridden using a user-defined signal handler. Okay? And for single-threaded processes, okay, the signal is delivered to the process itself. The issue here is, what if you have multiple threads running in the process and signal is received? To where will the signal be given? Let's have an example. So, of signals. Okay? The way to send signals to a process is via the kill command. So the kill command will send a signal to a process. If you want to stop a process, for example, you can use the kill command to terminate a process. So we actually have okay, so signal. So overview of signal. Okay. So again, mostly from the POSIX standard. The different types of signal. So, okay, so these are the listing of some of the standard signals. SIG HUP. Usually, the signal name is prefixed with SIG. SIG interrupt. So we have to kill a process, to force kill a process, kill -9, or kill minus SIG kill, and then you kill the process. So I have here an example code. Okay, so this code will override the Ctrl+C handler. Remember that when you run a program and then you press Ctrl+C, the program will stop. Okay? So here, what the code here is, you have SIG interrupt, then you specify the signal handler, and then you have a loop here, infinite loop. And whenever we press Ctrl+C, instead of just quitting, it will output something like this. Okay, so let's try this. So the program now is in an infinite loop. And when I press Ctrl+C, normally if you don't override the default signal handler, the process will just stop. But this time we override the signal handler for SIG interrupt, and it will output, it will trigger the, aha, you pressed Ctrl+C. That means we were able to override the default signal handler. Okay? It's actually the signal system, the signal function that does that. Okay? Now, in this example, we only have one process. We have a process with a single flow of control, a single thread of control. So it's the process itself that processes the signal. Now, when it comes to threads, there might be some complications. Okay? So the question is, where should a signal be delivered for multi-threaded processes? And we have several options. The first one is to deliver the signal to the thread to which the signal applies. So you can actually specify in a thread what specific signal that thread can accept or can process. So if this particular thread explicitly stated that, okay, I will receive the signal, then when that signal is received, that will be forwarded to that particular thread. Another option is to deliver the signal to every thread in the process. I don't care whether the thread explicitly stated that it will process this signal, but I will send it to every thread in the process. Another option. Third one is to deliver the signal to certain threads in the process. So just a subset of the threads in the process. So you can do that also. And the next one is to assign a specific thread to receive all signals for the process. So there is a dedicated thread that is just responsible for receiving signals, and then it will process that signal. Okay. The main reason for so that's signal handling. Okay. Next is thread cancellation. So okay, we have threads running, multiple threads, and at some point we would like to cancel a thread. Why do we need to cancel thread execution? An example of this will be in the browser. When you open a page, okay, a web page, normally there will be multiple threads that will render the content of the page that was downloaded. For example, you have an HTML page. That HTML page contains just plain HTML and probably some images, right? So normally you have a separate thread that will fetch the image and then render it on the browser. Now, what if you press the stop button on the browser? So what will happen to the threads? So the issue of thread cancellation will need to be addressed also. So how do we do thread cancellation? So it's basically terminating a thread before it has finished. The thread to be cancelled is called the target thread. And there are two approaches. The first one is called asynchronous cancellation. So it's just immediate termination of the thread. So remember that the thread is a flow of execution. So when a thread is cancelled, it stops there, and you don't know what will happen. That's asynchronous. The second one is deferred cancellation, which allows the target thread to periodically check if it should be cancelled. So the cancellation will just inform that, hey, thread, you need to cancel. And the cancellation is not immediate. It can do some checking first, and if it can now cleanly cancel or terminate, the thread can cleanly terminate, then okay, that will be great. So that's deferred cancellation. And in the pthread API, we have the pthread_cancel, which allows the cancellation of threads. So let's say there's a pthread that renders the image on the web browser, and then you press the stop button on the web browser. So the thread will have to cancel. So we have this pthread cancel. So when the event button is pressed, the stop button is pressed, then it will send a message to all the threads to cancel. Okay, this is an example. And this one is particular to pthread. So remember that pthread is a popular, is a widely used thread API. So most of the ideas regarding threads are implemented in pthread, which is actually used or implemented in different operating systems. So in pthread, invoking thread cancellation request, the cancellation will depend on the thread itself. So actually on the state of the thread. Okay? So you have, again, you have two options. You have deferred and asynchronous. And by default, I think in pthread, you have deferred cancellation. So even though you cancel a thread, it does not immediately stop its execution, but rather it performs some check until it can actually stop its execution. Okay? And usually we can check, okay, for cancellation using this pthread underscore test cancel. Okay, so that's the idea on pthread. It's by default, you can set the property of the thread, of course, but by default it deferred cancellation. So on Linux systems, thread cancellation is handled through signals. Probably I'll upload some example code for this. I haven't created a code yet, but I will upload a code for thread cancellation probably this weekend. Okay. So that's thread cancellation in pthread. How about thread cancellation in Java? So I don't know if you programmed a game in Java and you need to cancel a thread. So normally we have the in Java we have the interrupt, which interrupts a thread, cancel, and then there is a loop that checks whether the you can have a loop like this that will check whether the current thread is interrupted. Normally you see this code in animation. So let's say the game ended, so you have to stop the thread that renders the animation. So usually the code fragment that you will see kinds of multi-threaded applications. Okay, so that's done. Thread cancellation, the issue on thread cancellation. The next one is thread local storage. So thread local storage is another issue which allows each thread to have its own copy of data. Okay? It's useful when you do not have control over the thread creation process. So remember, if you're using in Java, if you're using the executor service, you don't actually have control of the local storage, right? Because you don't control the thread creation. Simply tell the executor, this is my task, run it on the thread that you're managing, right? So sometimes you want the thread to be able to access data. So we have TLS, or thread local storage. And it's different from local variables because local variables are visible only during the single function invocation. So after that, it's gone. Right? So remember, in 131 you have the stack frame, or in programming in 124 you have the stack frame or the activation record. And once the function returns, then that activation record is gone already. So that's the problem with local variables. Okay? So thread local storage is as important. Okay? And it's similar to static data. I think I have an example here. TLS.c for the pthread example, for the pthread API. So just lifted this from the web. So you have this. This is the variable that the key, okay, that you're going to use, and that key is used to access the thread specific or thread local storage, and get this key. This is the code that executes in the thread function. So each thread will have its local copy of its own local copy. There's an example. Okay, so you create the thread, then you join the thread, and you access in the thread function the local storage, which is the key. So if you want to set specific value for this variable, for this data that is unique to the thread, okay, So you use this set specific function, the key and the TL, which is the value here. You can actually change that. Okay? You can experiment with this function and examine how to change to assign, to make a specific value or local variable for a thread by this manner. Okay, so that's thread level storage. And the next one is schedule. Last issue is scheduler activations. Now, most thread models actually use a one-to-one model, meaning one user thread to one kernel thread. But in certain cases wherein you have many-to-many and two-level models, okay, so it requires communication to maintain the appropriate number of kernel threads allocated to the application. So remember that there is sometimes you have to manage the number of kernel threads that you allocate for a particular process. And if you're using a many-to-many or two-level models, the question is how many kernel threads am I going to allocate? Will it be a fixed number, or what particular value, what particular number of kernel threads am I going to use for this process? Okay. So a solution is to create an intermediate data structure called the lightweight process, or LWP, which actually will just facilitate the communication between the user thread and the kernel thread. Right? So LWP appears to be a virtual processor on which the process can schedule user thread to run. So this is how it will look like. So you have kernel thread, you have the lightweight process, and then you have the user thread. Okay? And each LWP is attached to a kernel thread. And the question is how many LWP will be created. Okay? So the mechanism here is if a user thread blocks, okay, we need to create additional. We have to inform the kernel, okay, you need to create additional kernel thread and additional lightweight process. So scheduler activations provide app calls, which is a communication mechanism from the kernel to the app call handler in the thread library. So the idea is to provide a communication between the user thread and the kernel, wherein they will be able to allocate the desired number of kernel threads for them. So that is the idea, and the communication is made using an app call handler, app calls. That's scheduler activation. Next is, okay, so we've addressed the issues regarding threads, other issues. Okay? So we now look at the implementation of threads in some operating systems. So the first one is the Windows threads. So the Windows threads again provides a Windows API, which I demonstrated before. You have a create thread function, okay, and implements one-to-one mapping, one user thread to one kernel thread, and each thread contains a thread ID, the register set representing the state of processor, separate user and kernel stacks for when thread runs in user mode or in kernel mode. So normally each process will have will have a user stack and a kernel stack. So here the same also for the thread. Remember that stack is unique to a thread. Okay. And provide private data storage area used by runtime libraries and DLLs. Okay. And collectively, the register set, the stack, and the private storage are known as the context of a thread. And if you look at the data structures associated with the threads in the Windows, we have actually three data structures. Most of the time, what is manipulated in the user space is the TEB, or the thread execution environment block. But we have eThread, which is called the executive thread block, which includes a pointer to the to process to which a thread belongs to, and to a K thread in the kernel space. So there there is no direct one-to-one kernel thread to user thread mapping, but rather we have a levels of indirection. So first we have the E thread, who knows the corresponding kernel thread for that user thread. And then we have the kernel thread, which is responsible for uh, maintaining information about the scheduling and synchronization. Then we have the TEB, right, which is the one associated to the user space. So if you're going to look at the diagram here, so you have the main, let's say the main thread, kernel thread, right? And it has a pointer to the process, to the actual process that owns this kernel, this thread. Then it has a pointer to a kernel thread which contains information about scheduling and synchronization. And then the separation here, right? We have the pointer to the associated user thread, right? And you have this information. So two levels of indirection in the kernel space. So that's for Windows. As for Linux, okay, Linux actually is interesting because it does not somehow differentiate the idea of process and thread. But in traditional operating system, we have the process as the high level abstraction. But in Linux, it seems that the high level of abstraction is a thread or a flow of execution, and then it actually simplifies things. Right? So Linux refers to them as a task rather than threads. So there's a data structure in the Linux kernel called struct task underscore struct, which describes somehow the unit of execution. And the creation of the thread is done via the clone system call. And the clone system call allows a child task to share the address space of the parent task process. And there are certain flags that control the what will be inherited by the child process, or actually the child tasks. We don't talk about processes in Linux. We talk about tasks. Okay. So different example here. So if you look at the man page of the clone system call, it's actually the one used to implement fork. So clone creates a new process in a manner similar to fork, okay? And that's how Linux does this. Unlike fork, clone allows the child process to share parts of its execution context with the calling process, such as the virtual address space, file descriptors, and signal handlers, right? And let's have an example. I think we have an example here by VI Linux Clone. So in this example, okay, we're going to create a thread. So we have the main function here. And we're going to create a thread by using the clone system call. we have here this code, this call to the clone system call, and the function that will be executed in the thread for the particular or the task for the particular the task, the function that will be the thread function. You can think of this as the thread function that will be executed by the thread. So try that. So gcc -o linux clone. So this is the default clone. It's not yet the. So here you see the event that happened. Okay, so you have the child sys buffer hello from parent, child exited the status buff equals hello from parent. Now this is the code that actually creates a thread via clone. So vi via clone. Okay, so what it does is to, in the clone system call, you specify what specific information from the parent process will be created or will be inherited in this particular process. So here we explicitly state that, okay, when you clone this process, you inherit the signal handlers, the file system information, the virtual memory, the files, and this one is clone thread. So remember, we have the option whether we want to clone the threads, okay, or during the fork, in the issue about duplicating the thread. So we can specify that in the clone system call. So here we have by this. And so this one will display the information. So it says here that this process PID is 2561, creating a new thread. The thread PID is 2562. Hit the screen. So 2561. So ES. So you see here the information that this process, right, will have the same PID. These two, we call this the thread ID. Okay, so remember that the thread should have the same process ID as the, in Linux, should have the same process ID as the parent process. So we actually have two here, 2561, which is the same process ID for the two threads that was created via the system, by the clone system call. Okay, so that's the idea, and yeah, that's how Linux. Okay, that's how Linux implements threads. Okay, via the clone system call, but you simply specify the what particular parts of the parent process will be duplicated to the thread. Okay, so that ends chapter 4. Okay, so do you have questions? You can post something on the chat. Currently there are 18 students online watching this lecture. If you have a question, you can post them. These 18 viewers, if you have a question, please post some chat box. Okay. Now, in our textbook, the next chapter is actually CPU scheduling, but we're going to skip that chapter for now. Instead, we're going to move to the chapter on synchronization, because synchronization is actually related to the threads. So I'll give some overview of so we're going to skip chapter 5 for now. We're going to finish synchronization first, because this week your laboratory is all about implementing a solution to the dining philosopher's problem. So we're going to look at synchronization. So remember that in threads we have multiple threads of execution, and at some point they might access a shared data and modify that shared data. So there might be some problems with that, right? An example that I would like to share to you about synchronization is ICS is conducting webinar series, right? And our task, me and Mamiya, is to write a script that will automate the sending of certificates of participation. So we have a Google form. Then after submitting the form, the certificate of participation should be automatically emailed to the one who recently submitted the form. Unfortunately, if there are a lot of people simultaneously submitting the form, okay, a problem arises in the script, and there are inconsistency. An example is that multiple emails are sent to the participant. So that is an example of a synchronization problem. We have a single form and we have a single script that will send the certificate of participation, and then if a lot of people simultaneously access that script, then inconsistencies can happen. And that's why you have systems like that. You need to understand and implement synchronization. We're actually trying to fix that bug. We're still actually fixing that bug, but probably using what we call the lock service from Google Apps. Anyway, just as an example of a real world problem wherein synchronization actually needs to be handled. So here we have some techniques. Just an overview of some of the techniques that we're going to cover in a thread synchronization. And probably in the lab this week, you probably used mutex locks in the pthread API and semaphores also in the pthread API. Okay, so we'll discuss them later in progress in this chapter. Okay, so for the objectives. Okay, so to describe the critical section problem, okay, so what do we mean by critical section? Okay, and what is a race condition? Illustrates hardware solutions to the critical section problem, like memory barriers, compare and swap, other hardware solutions. Then we can also have software solutions like the use of lock, semaphores, monitors, and condition variables. And we're not actually looking at the actual problems here yet, but still more on the tools that are needed to solve the. It's actually chapter 7 that discusses the specific problems. Chapter 7, that is where that's where dining philosopher's problem is. We're just going to look at some of the tools that we're going to use for addressing synchronization problem. Okay, so we'll stop here and study for your exam. I haven't started writing the exam, but later today I'm going to start writing the questions for the. So that's all for today. Thank you for joining me.